should add the thesis was completed. My supervisor at the time said, you don't need it and it would take a year to do, and he was right on both counts. But 40 years later, I thought I should finish it off. Right, well, sorry, let's talking about differential catchment analysis, which we'll explain, and I'll put it down as a battle between signal and noise, because out in the bush, noise is the sort of random fluctuations you get, but there are overlying signals that can come through that noise. So our aim is, in this is to use field data to get a sort of a theoretical handle on how little catchments perform, and in particular to look at the groundwater hydrology of textbooks and sort of try to apply it to a field case and see whether it works. And I suppose I'd say it's a bit of a long journey through some obscure areas, but it does, I think, give an interesting picture at the end. And I suppose when I say it's poor but my own, I've been a bit shocked at looking at it 40 years later down the track how little work that's been done in this field since we did this introductory block of work. And really comes across as the area needs a lot more intellectual work. Another one that comes across is the so-called dominant catchment shape in Australia, which we'll talk about. It really hardly gets a mention in the literature. There's lots of empiricism in field measurements and projects, but very little theory. And this actually centres around, a lot of this centres around what's called double-peaked hydrographs, in which the peak flow occurs days or usually many hours or days after it stops raining, and they really hardly figure in textbook hydrology. Hydrologic vehicle for this is called Cropper Creek. It's up near Myrtleford. Paired catchment projects. There's 3 small catchments side by side. It was under native forests from 75 to 80, and we've used the data from this period simply because all the catchments had the same land use at the time. One of them was converted to radiata pine in 1980, and that's looking down from, if you like, the head of the catchment down the flanks. So it gives you an idea of the shape. That's the ridge. And you can sort of get an idea of the size. There's a riparian strip left. It's had a lot of studies on hydrology in that time. Let's just looking at the catchments, 3 small catchments, Betsy Creek at the top, Ella Creek in the middle, and Clem Creek down at the bottom. Basically, we'll talk about this sort of the bowl-shaped heads, which is this area. That's right. People can't see it, sorry. Use your mouth, sorry. There's just a photograph of the clearing in the 1980. You can't do that now, but you could then. Pushing over the heavy forest. It's planted up with radiata pine, Clem Creek. The catchment to the right is Ella Creek. The area was burnt in 2006 and has since been replanted and got a second crop. Should add that there'd be some brilliant hydrographs being generated in the last week up there, and they're still measuring. So if anyone actually looks at them, what we're talking about today would really be coming through right at the moment. The double peaks and all of that would be being shown very nicely. Done a lot of studies there, pile conversion, nutrient balance, fire effects, groundwater processes. The slopes act like a rechargeable battery, so that when it rains, the slopes fill up with water. That water finds its way to the stream. As the water is either transpired or goes off to the stream, or perhaps goes right down into the bowels of the earth, the slopes lose their charge, if you like. There's very little surface flow. You can show that the mechanism of storm flow response is almost always groundwater. The major storms we're talking about here, they're long, low-intensity winter events. If you look at a textbook, it will always have a nice little block of rainfall. In fact, what happens here is that the rainfall is sporadic bursts that go on over 3 or 4 days, and often never entirely, they fade away rather than just suddenly stop. The streams are small and they're rough and they're turbulent. If you change the flow somehow or other, the effect travels downstream like a little train. In fact, it is actually like you can actually make a discontinuity in flow, and you actually walk along and follow that discontinuity in flow at about 2/3 of walking pace. So although the streams are rough and turbulent, things don't get transmitted downstream very fast. In the earlier work, we actually measured the responses of the streams to rainfall as you went upstream, and found that as you went upstream, the response became much more subdued, much smoother. And we also looked at the groundwater assumptions of groundwater theory directly and found that they were approximately met. And we'll meet this word approximately in due course. Talking about hydrographs and hyetographs, and we'll look at one of these a bit later, but a hydrograph is a record of stream flow with time, so there's one there. Hyetograph is a record of rainfall intensity with time, so the orange or the brown one at the bottom is the rainfall intensity in millimetres per hour. And you can see the streams go up when it rains and eventually go down. Our data set was 23 large storms in this 75 to 79 period, so we used all the storms that were big. Should add that we're going down a path of hydrograph analysis, and John Hewlett, who was a doyen of forest hydrologist, quipped one day that it's the last resort of the desperate hydrologist, and I think he's right. The data's on an analogue form recorder, roll charts. Should add that you actually see things on the roll charts much better than you do in the electronic data, I've come to the conclusion. And the roll charts, many of the effects we're talking about are very evident when you look at them, but when you put them on the electronic forms where the axes are compressed, it's hard to see them. So I quite like the charts, except that when you digitise them, you get digitiser shakes. You get delirium tremens and essential tremors and what have you come across as another source of error. So I think roll charts are good, and very time consuming. Double peaked hydrographs, there's just two examples, and you'll see Ella Creek is the bigger one. Clem and Betsy Creek are about the same size. Not all storms are uniform across the catchment, so that you do get some variations from just due to the input. You can see the rainfall intensity. You see what I mean about the storms of long periods of uppy and downy rainfall. And in particular, draw your attention to the delayed peak on the right-hand side for Betsy Creek and Clem Creek, particularly Clem Creek. You can see that it stopped raining, but you don't really reach the peak until 2 days later. And that's the sort of thing we're talking about. Give you a little bit of a background about theoretical groundwater hydrology. And in this, you're sort of assuming that the aquifers, the slopes that carry the water are continua. And we'll come back to the concept of continuum, or continuums, or continua. But one of the assumptions is that you can sort of infinitely subdivide them, that you can halve the distances and you get half the result, if you like. That's not quite true in this case, but you also assume that properties can be defined at a point, and that's true, but one of the things we concluded is that point can't go below about 10 metres by 10 metres by 10 metres. In other words, taking a laboratory sample is not representative of the continua. You have to be much bigger, and that's a major issue. They're called water table aquifers on the slopes, and what we mean by this is that if you dig a hole in the slopes, eventually we'll get down to the groundwater table, and that's the water table aquifer. The groundwater slope the groundwater flow is about proportional to the slope of this phreatic surface and the thickness of the aquifer. That's the assumptions. And the result of putting all of this is a set of partial differential equations that need initial and boundary conditions. And there's a well-developed theory, but it's rarely applied out in forestry cases, or indeed any cases. So why are we doing this study? And I think come to the conclusion that if forest hydrology is to make that the great leap forward, it really needs to get an overview. And what we've been doing in the past has been glorified case studies, and they've been good and met their aims, but need a more theoretical approach. And I'd like to say that this is a small step in that direction. Thought we might just look at some other disciplines of getting a theoretical approach. I think the argument is that if you want to advance the disciplines, the best way in the end, it removes a lot of the need for drudge work. And a lot of forest hydrology work is drudge work, where you're out in the bush and you've got noise and it's wet. Error-prone trials are expensive. You've got to go miles away from anywhere. Anyone that's done forest hydrology will be able to relate to that. Theoretical work is faster, more elegant. It often gives clearer, better answers. And if nothing else, it makes field work much more directed and more efficient, because you're actually measuring what you should measure. Thought I'd look at two examples, and the first one I've taken is the Wright brothers and Aeronautics. Wright brothers came up with the first workable flying machine, in fact the first, and then later the first practical flying machine. They came out of nowhere from the scientific point of view, so they were greatly resented by the American science establishment, and so they viewed them as so-called bike mechanics, but history has been a lot kinder to them now, and looked at the work and now views them as probably America's two greatest scientists, and certainly in terms of economic impacts. So the Wright brothers did a lot of wind tunnel work, and I've just reproduced some photographs from their early wind tunnel devices. They based their flying machine on careful wind tunnel testing. The picture there is the first flying machine about 110 years ago or something. And although, as I understand it, wind performance is not entirely, or flying is not entirely understood, there's a very large practical body of knowledge. And if you were designing a flying machine these days, you would rarely go back to wind tunnel. You'd just use a computer simulation that embodies the knowledge. And what we're sort of saying is that this overarching knowledge has removed the need for all this drudge work in wind tunnels. I'm arguing that forest hydrology is about the same as where the Wright brothers were with their wind tunnel testing, empirical work. And might be well done, but we don't have that overarching body of knowledge. And the second example I looked at was planetary motion, and you had all these people like Tycho Brahe and observers, and they went and studied the stars, and then people like Kepler and Galileo came along with, made rules of planetary motion, which laws, if you like. Newton came up with an overarching theory of gravitation that sort of explained it, and the laws are well enough established now that if you're going hunting for planets, for new planets, you start looking for perturbations from the Galileo's, from Kepler's laws or what have you. If there's a perturbation, there's a good chance there's a large mass causing that. I'm arguing that we're not much better than Tycho Brahe was with his observations. We don't have that overarching laws. Perhaps we're a little bit better than that, but we're certainly nothing like the overarching theory that does it. So hopefully we might move this way in the future. So what's this got to do with forest hydrology? Some, but not much overarching theory. We've got sophisticated field trials, we've got monitoring, but it's laborious and expensive. Error bars are always big. It's hard to put our results into a numeric pattern, and you can't use the astronomic technique of going looking for deviations in the numeric pattern to say, well, this is happening. And I've been a bit surprised and perhaps a bit horrified that there hasn't been much movement to a theoretical base in the last 4 years. Unfortunately, what we're talking about has got some arcane mathematics, so I'll have to give you a little tutorial. First one is this word approximate, and I've been cheated here because I've used it as a get out of jail free card. So you'll say, oh, if there's a problem, you'll say, oh, it's approximate, and leap off and not consider it further. The assumption is that a small change in a small deviation in some factor leads to a small change in output. And giving you an example there of a circle or a ring that sort of approximates a circle, and then the question, does an equation like area equals pi r squared, does it work for that irregular shaped thing? And you sort of say, well, it approximately works. And what do you mean by approximately? And I guess you could set error bars, but we'll use that word approximately all the time, but we probably will never get round to defining the error bars. Second thing is that Euclidean geometry. Now, I don't know much about Euclid, but I gather he was a Greek guy and he came up with the concepts of circles and straight lines and Euclid's elements of the famous books in geometry. And I suppose go out the bush and say, well, find me a circle, and can you find a circle out in the bush? I suppose if you've got a background in forest harvesting, you'd cut a tree down and say, well, there's a circle, but it's a pretty approximate circle. Can you find straight lines out in the bush? And you sort of can't. And all our maths is based on Euclidean geometry of circles and squares and triangles. But you know, they don't occur out in our forest, but I'm not clever enough to come up with anything better. Thirdly, we'll be talking about differencing flow sequences with time. I'm just series 1 and series 2 are two little parabolas which I've just plotted, and I've plotted them with a bit of error. So it's it was ax squared plus b plus a random error. And then you can see that if you add the two parabolas together, you can see the error is pretty tame. You've sort of got the result. But if you difference them, can you see that you've suddenly enhanced the relative error greatly? And I've just expanded down the bottom a small portion of that plot. But what we'll be doing today is differencing waveforms. And as soon as you difference them, you get a whopping increase in the relative error. So you just might bear that in mind in evaluating what we've done. Partial differential equations. I think Newton, came up with them in the first case, and they've been a staple of mathematics. So mathematicians like Euler and all these guys, Bernoulli and what have you, all played with them. In this case, the rate of change of height with distance squared, if you take the rate of change of that, equals the rate of change of height, groundwater height with time, plus V charge per unit area. And there's a few constants we've chucked in. So that's the form of a differential equation. You actually have to say what it was like at the start, which is the initial condition, and you've got to say what's happening at the edges, and that's the boundary conditions. In my past work, we did actually solve the differential equations of groundwater theory, but it's a lot easier now than in the 70s, I have to say. I used the so-called Wolfram language, or package called Mathematica, in fact. You branded themselves as Wolfram language. ND-solve, which is a numeric differential equation solver. Not always possible to get solutions for various reasons. I've used the Trock variant of the Boussinesq groundwater equations, and that allows different shapes to be handled in Cartesian coordinates in a way that we'll look at. Trock did this quite brilliant work about 2003, which they took the Boussinesq equation, called it the hill slope storage equation. The original approach goes back to the French mathematician Joseph Valentin Boussinesq, 1842 to 1829, and in that we haven't shown various constants, but they're there somewhere. Do have some reservations about numerical solutions of PDE, so it's sort of like a sausage machine. You just shove in all the stuff and you turn the handle and out comes your solution. And I sort of worry that putting a PDE solver in the hands of a physicist is a bit like sort of giving cows guns, and you get a result, but not necessarily quite what you want. And you think, well, perhaps mathematicians should be doing the PDE solvings. But having said that, I guess if you're a physicist, you think, well, I've got to do it. No one else is going to do it, so you do it. But there are reservations, which we're just addressing at the moment. Right, that's enough of that. our catchments is a geographic shape. And the left-hand graphic is just a view of our catchment, and you can see the top bit, the head, is, if you like, got a semicircular geometry, and the catchments actually have to fit together. In other words, there's one behind it going the other way and one alongside it. So I've actually given it a bath edge top, if you like, and which they sort of, when you start looking at them, they do actually have something like that they all have to fit together. Then as you move down, you've got the flank, which is a sort of just a parallel bit. And then at the bottom, you sometimes have if the top is convergent with water flowing down to a point, the bottom is divergent. And the divergent areas also figure in hydrology, but they're much less common out in the bush than convergent or flank. The troc one I used is on the approximates the circular thing or approximates everything by strips of slightly different geometry. So you can see that what we've actually done is make our convergent bit like a fan, a whole lot of bits of tapering bits put together. Question is, how well do these regular geometric figures fit our catchment bits? And we looked at the flanks at Cropper Creek, and you can see that we've got distance, and the height above the stream is a function of distance from the stream. And you can see there's a lot of scatter. The lines are the points because we did this using a contour map. And I think we've got a correlation coefficient of about 0.75. So it's sort of saying, look, the model of just if you like, a V parallel shape fits the data reasonably well, but it's not terrific. And when you go up to the head, which is, we're saying, a convergent bowl shape, it actually does either better. It's about 0.95. So the head is more approximating a conic section than the flank. But when you actually look at the contour plan of the head, which is the one on the far right side, you can sort of see that, yes, if you like, you can superimpose your catchment plan of the head on a conic section, and it fits, but it's a very irregular piece of the conic section. It's not a nice, even piece of the conic section. So again, we get back to this word approximation. There's our three catchments. We've taken them off Google Earth. You can see Betsy Creek at the top, Bella Creek at the bottom, and Clem Creek down the bottom. When the data we're using was there, Clem Creek was under native forest. Giving you the small view of the catchment, you can see the head and the flanks. And basically the convergent head, if you take the blue line where the stream starts, perhaps go a centimetre, so perhaps go a few degrees, so a few hundred metres from where the stream starts, and that's probably about the bowl, the focus of the convergent head. There's our Koch equations, which you won't see again, but basically that's what it looks like. That's what you're solving. Shove it in the sausage machine and put it a bit like this. So you've got the various inputs, which is your domain, your spatial recharge, which actually is the rainfall, constants porosity, hydraulic conductivity, bedrock slope high. You've got the initial condition, which you're putting in. You've got the upper boundary condition, which is what's happening at the top end of the catchment. You've got the lower boundary condition, which is what's happening at the stream. You've got the catchment shape, WX, which is the width of your strip as a function of distance from the stream. Shove it in the sausage machine, turn the handle, and in some cases you get a solution. In other cases it won't solve because at some point it starts dividing by zero and everything goes to infinity. So that's pretty much what you do. The question of whether your solutions are right is a great question, and still working your way through that. Since you're solving these equations numerically, it's very difficult to quite know that it is producing exactly the answer that it should be producing. Just looking at our groundwater theory, our initial and boundary conditions, you can see that at the stream you've got a line of symmetry because you've got a a slope the other side, but also feeding into the stream, so that gives you a line of symmetry. At the ridge, you've got a line of symmetry because you've got a catchment the other side doing the same thing. Our equation relies on the stream being the lowest point, so that it's assuming that there's nothing happening below the stream. This is actually one of the points of assumption, and it's not quite correct. You've got at some point an initial level of groundwater storage. Our slope distance from the stream to the ridge is perhaps 400 metres, and the slopes are 20 degrees. So as you get further and further away, you're suddenly the groundwater action is happening 10 and 20 and 50 metres below the ground surface. And that makes it very difficult to measure. And that's one of the reasons people don't do much work in this field, because measurement is so difficult. And just pinched a little graphic from a website on groundwater solutions, and just a photograph of one of the streams. And you can sort of see that your theoretical, so your textbook has a nice regular diagram, but when you actually look at the stream case, it's just a bit more difficult. And you can get over this by averaging and what have you, but it's not always quite so simple. Anyway, solving ad hoc equations for our convergent geometry, and you might just have the visualization of at the top right is top is our convergent slope, remembering we're dealing with sections. You might imagine putting a whole lot of cows uniformly across the slope, and then opening a gate, and then measuring how many cows come through the gate as a function of time. And it's actually quite analogous, and that's actually a photograph of cows going through a gate that the ABC were nice enough to find me. But what happens is that the outflow is a function of time. You can see the input block of rainfall, and you can see that our convergent geometry gives us a very delayed peak, because what you're getting is the infiltration at the upper slopes, and then it has to come down to the lower slopes, so it takes a day or two to go down to the underground to the lower slope. So you get this very delayed peak. And you can see it there, that's where our case. And you can actually, as I said, you could actually model it in principle with cows going through a gate if you were that way inclined. Looking at it for the parallel and divergent cases, again, putting your cows there, but you can imagine if the cows are moving downhill, the rate of cows going through the down is going to be quite different, because you haven't got that big convergent area passing water in. So there's the solutions you get for the parallel and divergent cases. And when you actually put them together, so this is our three solutions we've got for this case. You can see that the convergent case gives you a very delayed peak relative to the parallel or the flank case, or the divergent case. And if you imagine, so there's your outflows, and you've got the rainfall, and the very delayed outflow. You'll also notice that when you actually, one of the issues which I'm just dealing with at the moment is in these simulations is that I've just got the rainfall effectively as a on-off. And you sort of get a hydrologic shock, which is that little spikiness when you suddenly shut the rainfall off. And in fact, you can actually find that examples where the data actually shows that when you get a very intense burst of rainfall, you sort of get a period of hydrologic shock after it, and then it settles down. Anyway, looking at it, how our hydrograph changes with catchment size, got 4 graphs. The lowest one, 30 hectare of convergent, 0 of flank. And so it's purely the head of the stream. And then as you add in 15 hectares of flank, or 30 hectares of flank, or 45 hectares of flank, you're adding in the outflows of the two different geometries, and you sort of see that you get a family of hydrographs that behaves quite differently. And you can certainly see the second one in particular shows this double peaked effect, this double hydrograph peak. That little plot actually mirrors the Cropper Creek Hydrology very well, actually. You can find examples of all of those sort of hydrographs at Cropper Creek. And so I guess that leads us to a theory that our Cropper Creek data is showing this sort of differential response from the different parts. So I've got some testable hypotheses there that the head of the stream behaves fundamentally different from the downstream flanks. The flanks will be in recession when the heads are reaching their peak, and that the propensity of these catchments to give double peaked hydrographs really reflects the groundwater geometry at work. So that's testable hypotheses. Everybody we've looked at that. It's just double peaked examples of double peaked hydrographs, not very like the ones we've looked at, but they do show similar features. So we thought we'd try to look at our data and do some what's called differential catchment analysis. And so you'll need to pay attention here. Wake up, wake up. So there's our little map of the area. And you can see that Ella Creek's bigger than Clem and Betsy. And if you look at, we've made this distinction between the head and the flank. What we're saying is that the head part is about the same size in each of the catchments, but the length of flank varies from catchment to catchment. So if you subtract, for instance, Clem from Ella catchment, you really get an area of flank. So if you subtract the Clem hydrograph from the Ella catchment, you really got a flank outflow. And then by doing some simple arithmetic, you can scale that up and then subtract it back, and you can get your estimate of what the convergent head outflow is. But we'll look at that a bit more. Differential catchment analysis, we've taken a map. You'll suddenly see that the divided into convergent bits, which are the bits on the left, and if you like, the flank catchments on the right. So for Clem Creek, you can see there's actually two bits of convergent, one right at the head and another bit just above the weir. Ella Creek and Betsy Creek have got the convergent bits. And then what's left is the flank. We've given you the areas. So Ella has 30.2 hectares, Clem 34.5 hectares, Betsy 32.8. So about a 30 hectare convergent head. Should add that you don't get a stream, in this country you don't get a stream until you've got about 30 hectares head. And then you've got the flank area and the area of catchments. So this is, if you like, our geometry. What we've said is that the Ella Creek hydrograph minus the Clem Creek hydrograph is the hydrograph of a portion of the Ella flank. In other words, take the Ella Creek hydrograph, subtract from it the Clem Creek hydrograph. Clem Creek's bit of convergent head plus a bit of flank. Ella Creek's convergent head plus a lot of flank. So what you've got is a hydrograph and a portion of Ella flank. Scale up the difference to get the full Ella Creek flank hydrograph. Subtract that from the Ella Creek hydrograph and you get the head outflow plus errors. And presto, you've decomposed your hydrograph. And that's what we're calling differential catchment analysis. So we've done that on our 22 hydrographs, and this is the sort of result you get. The time in this case is 15-minute increments. Flow is a function of time. The heavy black one is the Ella Creek outflow. And we've decomposed it into, if you like, the flank outflow and the head outflow. And you can see that the flank outflow carries the major peak. The head outflow carries the delayed peak. And we've done this storm 4, storm 16. You can, because you've got two small catchments, you can do it using either Clem or Betsy, and you get slightly different results, but they're not very different. So storm 16, we've just given you the separation using the Clem Creek differencing and separation using the Betsy Creek. Again, the heavy black one is Ella Creek. you can see the both give you the major storm responses due to the flanks, the much more delayed responses due to the head. And so there's some difference if Ella or Betsy's uses subtractant, but it's not really very much. And we've got if you like, we've got 23 hydrographs, got a whole lot of testable hypotheses which we've done, and we've showed that it pretty much conforms with our theory. Basically, this is the 23 hydrographs. The top is the head, and I've actually centered the delayed peak always at 1,000, so 1,000 hours. Everything is referred to 1,000 hours. You can see that the head goes pretty much, with some exceptions, the head reaches a slow peak. The flank, you can see, basically, which is the lower one, all the variation tends to be much earlier than the peak of the head. And so in other words, the flank is giving you the storm flow variation, the peak is giving you the convergent head is giving you the slow variation. It takes a lot of computing to do this, so quite pleased I finally got to the end. So what we're actually showing is that the convergent head peak is way behind the flank peak. The flank flow tends to decline while the convergent head flow increases. So in other words, the flank reaches its peak very early, relatively early. The convergent head reaches its peak 2 or 3 days later. Done all sorts of statistical tests, and it shows that separation would seem to agree with the hypotheses generated by our partial differential equations. And it really suggests that the partial differential equations that we've solved are very consistent with our hydrograph data. And we're still actually working our way through various hypothesis testing, but it's looking pretty optimistic. So it's been a bit of a long journey. So what have we seen? So what we're saying is that we've got Euclidean personality types. And so our catchment can be, and the first one is the convergent areas in the head, and they're sort of stable, slow, reach their peak a long time after. Sort of like Gerd here, you know, slow, stable. Would it be your model of yourself, Gerd, would it? Why? You know, sort of not instantly responsive, but slowly responds. The parallel, the most storm flow response, some stability. So most of the actual immediate response to rainfall is this parallel bit. And then the divergent areas which you don't have, they'd be the party animals of the hydrology world. They'd reach a peak very responsibly, and then that peak is dissipated. And what comes across is they're all overlain by a large random diffuser, which is the soil. And the soil acts to hold up the trees and to pass water down to groundwater. But it sort of acts like this big random diffuser with interesting properties. So that's the sort of picture we've built up of our catchments. And pretty much, as far as I can work out, it's fairly much mirrored in the data. So what we've concluded, our groundwater theory does apply. Responses in the field are consistent with theory plus noise, and a lot of that noise would seem to come from the soil as a diffuser. The so-called theoretical response is strong enough to overwhelm all the sources of noise and irregularities, and so it comes across as these double peaks. So in other words, there is a groundwater signal there, but it's pretty much buried. Very literally and metaphorically. Euclidean geometry is sort of applicable, and using these Euclidean shapes, it sort of gets us there, but I don't think we actually have any alternative, and that's one of the reasons why we use them. Obviously, if we're really clever, you'd come up with some alternative. But the catchments are not really regular figures, and so to use them is all the time approximate. And I've been looking for values of the parameters I might use for things like porosity and hydraulic conductivity in these deep slopes. Really find almost nothing in the literature to suggest what the approximate value should be. So people do play with it, as I do, and you might guess it. There was a feeling that we could, by optimizing, playing with different values, that you could come up with correct, so-called correct values. But we found that's too difficult. We've also found you get intriguing little hints, like one of the assumptions of the equations is that the groundwater outflow conditions, how deep it is, and we found that if you change that, you get whopping effects on storm flow. And I've been pondering whether, Gary, some of your the spike flows you get after bushfire is it's actually changed the outflow conditions. And it's not due to the changing the hydrology as much as just changing the conditions near the stream. And so that you suddenly get whopping outflows, that sort of thing. So it does give you some tantalising glimpses. So we have been thinking there's some sort of computer exploration you might do, but it's difficult. Problems applying theory, and one of the things that we have to do is average it. We say, well, let's not look at the little variations in our slopes, and the question of just how much averaging is tolerable. It's a great question. The continuum assumptions, I've come to the conclusion that imagine looking at the density of a piece of wood, and you take a piece of wood and measure its volume and measure its weight, and then divide the weight by the volume to get the density. And if you had a piece of wood that big, that's fine. If you went down to a centimetre, that's fine. If you went down to a millimetre block, would that be such a good, or went down to a 0.1 of a millimetre block of wood, would that be terrific? Or a 10 to the minus 6 millimetre block of wood, would that be a terrific way of measuring the density? And because what's happening as you go smaller and smaller, your assumptions of a continuous medium are being challenged. And I've come to the conclusion that for this sort of work, you really can't go much below perhaps 5 or 6 metres by 5 or 6 metres by 5 or 6 metres in your medium properties. Otherwise, you're getting into the, if you like, the microscale. And that's a big difficulty, because there's no way you're going to be able to take a 27 cubic metre of sample back to the lab to measure its hydraulic conductivity. You've got stochastic and temporal variations in parameters. Our groundwater theory assumes K as a constant. You can actually show it varies with depth. It's probably got a stochastic variation from point to point, and it varies over time. There's almost no knowledge of what these values should be at depth. Irregular geometry is only approximated by Euclid's theories. Rainfall is a difficult input, and many of the hydrographs, the rainfall continues right across the period where we're interested, so it will stop, and then you get little bursts of rain here and there, and then you suddenly get a big burst and you've got a whole new hydrograph. And the so-called unsaturated zone, or the soil and the upper rock, acts as a massive low-pass filter. So water does get through it down to the groundwater, but it's got its own set of properties. So if you want to persist, you could argue that our catchments are sort of a natural clock, and if you get the time difference between the peak outflow at, say, Cropper Creek Weir and the second peak, you've got a clock, you've got a natural measure of time. And so you could actually start simulating that and finding how that property varies with how that time should vary as you vary different properties. You can get information on deep behaviour by matching the time difference between flanks and head peaks with parameters in the formulation. I think hydrologist in 1904 came up with a thing called Buckingham's pi theorem, and it's a great piece of work, and it's been very useful in all sorts of hydraulics. So you probably know it as Reynolds number would be an example, or Froude number in hydraulics. Dimensionless groups, where all the things that involve time are put into one block of variables. It's a great way to attack problems to get a really good overview of them. And think, oh, I really should apply Buckingham's pi theorem to it. It leads you to the concept of similitude of models and scaling up and all of that. And again, well used in hydraulics, but not much used in hydrology. I think you would really need to look at how other people have used groundwater partial differential equations in similar cases and try to build new experience. And I think finally we need to probably get back to our deep field measurements of the slope hydrology. And it's the sort of stuff we were doing in the 1970s, but it's all fallen by the wayside since then. And I think ultimately if the disciplines to advance, it's really got to get back to that sort of stuff. So I'd like to think that if you did this, you'd get better experimental design, you get better conceptual design, you get better buffer strip design, you get a better approach to a range of land use problems. And I thought what I was doing was obscure, but I've suddenly got myself involved in the last couple of weeks in a land use court case involving salinity and deep groundwater recharge. It involves exactly some of these issues. So perhaps it's involving salinity and impacts of a plantation and on outflow and all of that. So perhaps there is some practical use to this sort of stuff too. Anyway, conclusions. Decomposition of hydrographs into head and flank is consistent with groundwater theory. You build up an interesting conceptual picture of catchment behaviour that's hardly been explored. Application's got lots of theoretical possibilities. Explains the so-called base flow behaviour of the catchments. And what it means is that probably for long periods of flow, when it hasn't rained for a long time, the flow is actually coming out of the convergencies. So all these little convergencies are giving you the sustained flow. And when it rains, most of the variation's coming out of the peaks, out of the flanks and downstream areas. The groundwater shape signal is strong enough to overwhelm the noise, although it does struggle from time to time. And the classical mathematical approach can be made to work in a forest, provided the error bars are big enough. And it's pretty clumsy to apply, but you can still do it. So there you are. Thank you for coming. Photographing me as I'll be in a couple of years. Yes.
Thank you very much, Leon. I remember a few years ago, Leon, using the hallway about the opportunity to actually get your head into something rather than, as a senior academic, having this and that and all these things to do, but able to bury your head into something. So it looks like you had that chance.
Yeah, so you can see how it improves.
This is what you look like before and after. Nothing much has changed.
Yeah, thank you for that. Yeah, so.
Anyway, any questions from anyone on the floor as well as those online? If you do have a question, you can please type that in.
Yes,
and we can read it out to Lynn. Sorry, Gary, you're going to need to speak into the microphone.
Talking about the peak out of that convergent zone and relating it to the cows going through the gate, that analogy, but wouldn't it be more kind of three-dimensional? So as the flow's coming down, it'd be like you got three-dimensional cows because that little constriction point would kind of be filling up, and then the water would kind of start coming out as free water on the surface.
Well, I suppose with the convergent thing, given that it takes a finite amount of time for what's upslope to come down, at the start there's not much water to leave the catchment because near the gate we've only got the infiltration out of that zone, but 3 days later you've got the infiltration over that zone that has sort of moved down, and so it sort of reaches a maximum and then declines again. And I suppose if you have your gate, assuming the gate's not terribly, you dumped all the cows here and told them to walk down, early on the cows will fit through the gate easily because there's not that many, and then as time goes on there'll be hundreds of cows trying to get through the gate, and then towards later time most of the cows are gone, so again it gets easy. I guess that's I'd like to try it, but I can't work out how I can get the cows on the slope. Yeah.
Always consider that a bit of a challenge. Any other questions?
Overwhelmed.
The students there, you've been heads into hydrology for 2 weeks now. So.
Overwhelmed.
Chris. Thank you, Leon. I enjoy that very much.
Good.
I'm curious to know what the species is. Yeah.
It's a wombat, isn't it? I typed in picture of a wombat.
Can you pass comment on the number of catchment studies in Australia that we have where you could apply your sort of analysis to test the same sort of differential catchment analysis compared to, the sorts of information that they've got in the US where they've got hundreds of experimental catchments to work with?
I did a study on how many catchments, sorry. No, I don't need to go there. I did a study on how many catchment projects there are, and I think you do it to any of them, but what it does, it needs you to be intimately involved in your data. And I was always critical of a lot of it, and to a certain extent still am, particularly electronic data things where it's just automatically integrated. No one actually ever looks at the hydrographs. So I think that's probably the thing, that you've really got to have someone that's totally immersed to the point of being obsessional with your data. And should add, I think the charts help this too, because by the action of having to digitize the charts, you're forced to look at them, unlike the electronic stuff where it just flows into a vast hard disk somewhere and you've got no idea what's there. And I did find out that I was a bit disappointed when I actually put these under electronic form. I found it very hard to see the effects that look so evident on the analog recording charts. So I think anyone could do it, but it requires a person with no social life, moderately obsessional. A good gatekeeper for the cows. Someone like me, yeah. No ambition, no social life, just plods along. Yeah.
Nobody made that connection there, Leon. Thank you for pointing that out. I have a question online from Tim F. Actually, a couple. To what extent do you think these approaches could be applied to urban situations where the presence of underground infrastructure, e.g. trenches, pipes, foundations, etc., complicate groundwater pathways?
Oh, well, I think it'd be exactly the same, except that you've got much more noise. The urban one gives you classic noise, but I think that if you've got rid of that noise, you'd still find the groundwater situation there, but you've got a much wilder. I think the soils give you a lot of noise. The irregularities in the soil give you a lot of noise. I think the urban one would give you a lot more violent noise. But I think the groundwater signal would be there. You'd need someone to have a go, but it does need someone to throw themselves into that data. And I think the other thing is that I found this very time-consuming to do, and clearly I can do it because no one's living on my super and all of that. But you'd need an organisation that would pay someone to really do this and not produce much output for a long time. So, yeah.
Also, another question from Ian Ferguson. Do you have a feel for the impact of the different personality zones on buffer widths?
Yes. Well, I've been thinking about that. If you're interested in processing stormflow hydrographs, the flanks would be the areas that must be protected. And if you have divergent zones, they would particularly need protection. The convergent areas probably really don't need much, but if you are sort of interested in the protecting the so-called sustained base flow, it's probably the convergent areas. So yes, it would require some thought on that one. I did actually do some work on that years ago, but I think the reviewers were unimpressed, thought it was going over the top.
Yes, question?
Yeah, thank you for this report. My name's Philip Kinghorn. I'm mainly involved with geology, groundwater and trees. So there's a huge, I'd say, lack of data on using geology and the soil types are dramatic in their had been walking around the last couple of days, which I were through forests and plantations and so forth, and just watching where the water's going and what's happening, especially if you've got those three catchments. Deep ripping has a dramatic filtration rates. The soil cover is another one. So I don't know how you put them together into one formula and say it's going to work. So I've got real issues on the plains with hydrology down there, where there's how do you understand pores, how you actually manage that. Got issues with surface water, as opposed to, as you mentioned, the base flow is dramatic, because it can basically, the base flow continues most of the year. That's a huge volume of water.
Well,
It's not
we never found, we mucked about with neutron flows and all this. We never found any hydrology in the top 4 metres of the soil. In other words, the water would just go through the top 4 metres of the soil down to greater depths, except, of course, right at the stream. And so we were never able to correlate anything that happened in the soil with the groundwater variation. It was happening 10 and 20, these are steep catchments, of course, so it's happening 10 and 20 and 30 metres below the surface. And we got the impression that the vegetation does influence it by dragging water up from the groundwater and transpiring and impacting on the, if you like, the initial conditions. But in terms of storm hydrology, the vegetation really didn't do much apart from hold the catchment together, which is a big thing. But I'm not sure if that's an answer to your question.
I just think it needs to be, well, basically the hydrology needs to be looked at. And I asked the question, is there any bores in that area? Like,
yes, the deepest bore, well, we're always trying to get people to fund deeper and deeper bores. The deepest bore we've got is 14 metres, which is about 50 metres from the stream. And that was above the phreatic surface, except occasionally in heavy rain, the phreatic surface would rise up into it. Yeah, we've got a whole lot of groundwater stuff on the lower slope, but we never had the money or the methodology to really go.
Appreciate the cost would be when it's not raining, really.
That's right. But we have actually published all of this, but we never felt that we really got a good handle on groundwater or the parameters or anything. But having said that, we've many years of groundwater measurement there.
So I know the practicalities, and I went to 3 areas over in Hamilton a couple of years ago, and they put in all the monitoring stations, and they had the 2,000 wiped out 2 of their stations. So the practicalities need to be worked on.
Yeah, we'd always would have liked to have done more, but and as I said, we thought we'd come back to it. That's probably
Interesting discussions. It's 10:30 now, so if there are any further questions or any further discussion, please join us and Leon in particular for a morning tea just now, and we can continue those things. Thank you very much, Leon, for coming along today. If you can show our appreciation for your endeavours.
And by the way,